First, we look at a theorem, central limit theorem. Whatever the population, the distribution of x bar, that is sample mean, so the distribution of sample mean is approximately normal when n is large. So in random sampling from arbitrary population with mean mu and standard deviation sigma, when n is large, the sample size is large, the distribution of x bar is approximately normal with mean mu and standard deviation sigma over square root of n. So consequently, we can convert x bar, the sample mean, to a standardized variable z. That would be the standard normal distribution. So this theorem is very useful because, like we said, not every distribution follows the normal distribution. But if we gonna talk about the sample mean, so we pick a sample and we try to calculate the average of the sample and the standard deviation of the sample mean, and that follows the normal distribution approximately. So not exactly, but approximately. So we're not going to prove this theorem, but we're going to use the theorem to do the problems. So again, if the distribution is not normal distribution, then we cannot use the normal distribution table. But since we have this theorem, central limit theorem, we can always use the table for the sample mean. That makes the problem a lot easier. Okay, so let's look at this example. In chapter 2, we talked about the number of items returned after Christmas. And suppose we recorded 30 customers, the number of returns of 30 customers. So that's like a sample from all the customers who returned items, and we have those numbers, and we did calculate the relative frequency. So how many customers returned one item, and we found out there are seven customers. So it's 7 out of 30 customers. That's how we got 0.233. Just to refresh your memories about this example. And then how many customers who returned 2 items, and we go back to the table, we count how many 2s, and so we did 9. We found out there are 9, so 9 out of 30, so 9 divided by 30, we got this. And similarly, that's the relative frequency table we did before. This is the sample size is small, so we may not be able to consider this as normal distribution, but we may not be able to pick a few samples to say that's normal distribution. But the relative frequency here is just it's a percentage, but it may not be exactly the probability for when you pick a customer randomly. Say, what's the chance of him return one item? We can say approximately 23.3%, but it's not because the sample size is small, so we cannot really this number 0.233 may not be too good. But if the sample size, we increase the sample size from 30 maybe to 300 or even more, 3,000, and we can do this calculation again, and the relative frequency number, we may be able to use it as a approximation of probability. Okay, so suppose we did this survey, and we did it to maybe 300 customers or even more, and we found out this. Actually, those are, again, it's the relative frequency, but if the sample size is large enough, we can treat them as probability. So this is like a population distribution for the number of items. So it's 1 the number of customers, the probability of of a customer who return one item is 25%. So it's 0.25 chance that this customer who return one item and the others. Okay, so the difference between the sample mean or sample that's you're picking like 30, you're choosing 30 customers to record the number of items who returned. So that's a sample. But how do you do population mean? Technically, you have to do a survey to all the customers. Suppose there are 3,000 customers who returned items. But if you pick 300, if you pick maybe 1,000 or 2,000, that's good enough. Or 1,000, that's good enough. Or maybe if there are only like 600 customers who return items, if you pick 300, and that's already half of the entire population. So that can be considered as a good maybe approximation. So here you can. So here the probability, we didn't say relative frequency because we did a very huge sample size, and that can be considered as population distribution. Okay, now we back to our question. So this is the example in the textbook on page 282, and so we have this table and population distribution. We can use the formula we learned before to find out the population mean. So multiply the value and its corresponding probability, and add them together, we got 2.61. So it's kind of like the average. So about what's the average number of items which were returned, and it's kind of like it's 2.61. So the average is like almost three items. So the average of number of items returned after Christmas is three. It's about 3, and the standard with the standard deviation 1.34. And so let's look at the question. If this year at a random sample of size 45 selected, what is the probability that the sample mean will be greater than 2.9 items? So this information here that was probably obtained before, maybe every year regularly. So if suppose they do this for the past few years, and that's the numbers they got, and so for this year, I can try to predict the probability of that the average number of items returned. So I want to figure out greater than 2.9 items. So it's kind of almost 3 items. So what's the probability of the sample mean will be greater than 2.9? So what's the probability of the customers, the average number of returns bigger than 3 items to 2.9 items? So what we do is, so when we pick samples, suppose we pick 45 customers, and we can do an average. So here we're not we're talking about the average number of items returned. So we pick 45 customers, and we try to we can of course you can record a number of items to return, add them together, divide by 45. But right now I'm just trying to do a prediction based on the past year's data. So you don't have 45 numbers you can use. Right now I'm just trying to do a prediction based on the previous data. So what I do is I use this data from before, this information from before, and I'm going to calculate. I can calculate the expected value, which is the average of average, because we're talking about average, and that's the same as population mean 2.61, as we explained before. So again, the formula we have before was this formula here. So expected value of population of sample mean is the same as population mean, and then we use these formulas to find out standard deviation. Standard deviation of sample mean is population standard deviation divided by square root n. So let's calculate that. So I have here standard deviation. This is population standard deviation. If I want to find out the standard deviation of the sample mean, that would be population standard deviation divided by square root n, and the sample size is 45, so divide by square root of 45 and do a calculation. I got 2.00. so this is standard deviation of sample mean. And then I'm going to use what we have learned before. How do I find the probability of normal distribution? Because we consider by the central limit theorem we explained before, this theorem, x bar is approximately normal distribution. So x bar is the average. So this average follows normal distribution approximately. So I can use the table to find the probability, the normal distribution, standard normal distribution table, probability table. So but again, x bar is not standardized variable, so we have to convert it like before. So x bar is greater than 2.9. We use the formula z equals x bar equals the standardized variable minus mu divided by sigma. So what I do is I take 2.9, subtract 2.61, and divide by 1.34. That's how I got 1.45. Okay, I didn't write this down here, but that's how I got 1.45. Convert 2.9 to z value 1.45 as previous examples. Okay, so one more time, it's 2.9 minus 2.61 divided by 1.34. You got 1.45. And, no, I'm sorry, 2.9 minus 2.61 divided by 2. Sorry, divide by, it should be 0.2. Let me make a correction. So I just made corrections that by using the formula to convert 2.9 to standardized variable, what we do is we follow the formula. 2.9, take 2.9, subtract the mean of the sample mean, 2.61, divide by the standard deviation of the sample mean, 0.2. Again, be careful. Why don't we use these values? Because before we said it's to convert a variable to standardized variable, we take the x value, subtract mu, and divide by sigma. But notice here we're not talking about x random variable. We're talking about the random variable x bar, the sample mean. So we have to use the expected value, the mean of x bar, and the standard deviation of x bar. But this sigma here is the standard deviation of x, not x bar. So we're talking about the average number of returns. We're not talking about the return of one customer. So that's why we have to use standard deviation of the average, which is 0.2 by the formula. And so we find out 1.45, and we convert x bar greater than 2.9 corresponding to z greater than 1.45. So we can use the table, but not directly, because the table is only for less than a number. So we can subtract it from 1 and look into the table. We found that the probability for z less than or equal to 1.45 is 0.9265, and subtracted from 1 we got 0.735. So this following part is the same as homework 6.29, 6.34. The new part is right here. When you use the formula is a little bit different. You cannot use sigma. You have to use the standard deviation for x bar.